we're recording now. So this is our last talk of the semester. Stay tuned. Our speaker today is Henry Segerman, who he's the master of all things three-dimensional. Every time I look at his website, I only feel dumber and dumber. So today I hope we can all feel that way by the end of the talk. Okay, thanks.
Well, thanks for the introduction, Randy. I hope that when my students look at my website, they don't feel dumber, but I guess I'll find out eventually. And thanks for the invitation to speak. So I'm going to be talking about two different projects that I've been involved with different sets of people, and they both have the sort of the goal of viewing three-dimensional manifolds from the inside. And so I'm going to be taking you through those two. And just before getting into all of that, let me just point out a couple of sort of earlier work in this area that I've done. So this one was sort of an earlier version of a system that let you walk around inside of a three-dimensional hyperbolic manifold in virtual reality. And here you're seeing that I'm walking around a square in Euclidean space, but here in hyperbolic space, it's actually a right-angled hexagon. And this is a sort of more recent version. You can see the graphics are considerably improved. And I'm going to talk about sort of the different possibilities of how you do this kind of graphics and how they work and what the advantages and disadvantages are. So the first project I want to talk about is raymarching the Thurston geometries with Remy Coulon, Subeta Matsumoto, and Steve Treadle. And if you get bored while I'm talking, then you can take a look at, so this website down here, 3-dimensional.space, has lots of videos and things you can play with. And we've also got our archive paper down here. Actually, let me just show you what that looks like. So this is the website, and you can sort of scroll down and find out about lots of different geometries. I think if you click things, then they play, and so you won't see very good frame rates from the videos that I'm showing on my slides, but you should see much better things in on your own web browser. Whoops, that is not what I wanted to do. That is what I wanted to do, and then we do this. Play slideshow window. Okay, so so what are the Thurston geometries? Just real quick, in case you're not familiar with what's going on here. I guess maybe the start of this is in 2 dimensions. Any 2-dimensional manifold, you can put a metric on it, put a geometry on it, so that it looks like the 2-sphere, the Euclidean plane, or the hyperbolic plane. And so then the sort of 3-dimensional version of this was conjectured by Thurston, the geometrization conjecture, and proved by Perelman and many other people. And it's a little bit more complicated, but it says that any closed 3-manifold can be cut up into pieces. The 3-manifold itself might not have some nice geometry of its own, but if you cut it up into pieces, then those pieces admit one of 8 different geometries. And those are the 8 Thurston geometries. And there's sort of various ways to group them. There's things that you would expect to see here: the 3-sphere, 3-dimensional Euclidean space, 3-dimensional hyperbolic space, some sort of products, and then there's these sort of 3 weirder ones here. And just to be clear about what I mean by a geometry, so we've got some sort of model space X, and then we've got a set of isometries that act on it. And to have a geometry means that, so for a manifold to have a GX geometry means that you have a set of an atlas of charts from your manifold into this GX geometry, where the transition functions have to be elements of G. So let me just sort of give you a tour of some of our visualizations in these different geometries, just to show you the kind of things that are going on, and then I'll say something about how we do these, how we create these simulations. So here we are in the 3-sphere with some, oh, there's the Earth. Apparently the Earth is in here as well. Here we are in H3. So this is, I think, the Seifert-Weber dodecahedral space. The geometry is quite different, of course. The first product geometry, S2 cross E. So actually looking down the Euclidean direction, and then maybe the way you can tell that something sort of strange is going on, that we're not in Euclidean space anymore. Well, if you look directly straight in front of you, you're looking down the Euclidean direction, and perspective sort of looks like it's doing reasonable things. Whereas if you look off towards the edges of the picture, you can see that things are sort of distorted. And that's because the light rays that you're seeing along are sort of doing interesting things in the S2 component. Here's another picture or another video inside of S2 cross E, and you can see the Euclidean direction is down here. And then off in this direction, you're looking along the one of the S2 directions. I think this one is actually, so that the cells here, if you imagine a dodecahedron being the S2 direction, and then you have a cell for each of the pentagons of the dodecahedron, and then you sort of cross that with an interval for the Euclidean direction. H2 cross E, similar sort of story. You've got the Euclidean direction sort of going this way, and then off in the distance here, you can see things are getting very sort of squeezed together. That's looking in the hyperbolic direction, or one of the hyperbolic directions. And then the three weird ones. So things get very difficult to interpret here. Well, let me just show you some pictures. So this is, we're inside of nil, and I guess maybe things look sort of reasonable nearby, but off in the distance in the background, you can see there's some very strange thing going on here. Maybe the sort of thing to think about is mirages or gravitational lensing. So geodesics are sort of reconverging and doing strange things in the distance. SL2R tilde is sort of like nil, but exponential rather than linear, so it's sort of even weirder. And here's Sol, which again is just very weird, and you can see some, occasionally you can see some sort of lensing sort of stuff happening in the distance here. So these are the sorts of things that we're generating. Yeah.
What made you choose the different shapes to put in the different geometries?
Oh, it's a very long and complicated story. So, I mean, in part, we have to be able to describe the shapes, and I'll get to what are the kinds of shapes that we can describe in the setup that we're doing. And then there's a lot of, you know, well, so many of them are take a manifold, and that gives you, by looking out into the universal cover, which is what you do, then you see the sort of lattice structure of that manifold. So often it comes from, you know, what's a nice manifold that we have. But then, yeah, lots of them are just, you know, is there something cool that we can illustrate about the geometry?
I see. So you use cubes here because you're showing how they twist around. And spheres wouldn't show that?
So it turns out that proper spheres are very difficult to put in the scene in the way that we're doing this in Sol. In many of the other geometries, it's very easy. In Sol, it turns out that we can efficiently do sort of horizontal and vertical planes. And so we're using those to make cubes.
I see. Okay.
Yeah, so there's lots of sort of interesting details about each geometry that affect things.
Thanks.
And this is Euclidean space again, but now we're changing the geometry of the space. We're doing some sort of Dane twist around the space and animating that whilst we're inside of it. So we can do this kind of thing as well. Let me talk about sort of different ways of drawing pictures on computers, drawing 3D pictures. And I'm first going to sort of give the distinction between two big sort of classes of methods that are used, which are polygon rasterization and ray tracing, and sort of raymarching as well. So let me first sort of describe polygon rasterization. So the vast majority of computer games use this kind of, and also like if you've used 3D design programs, they're most likely using this sort of technique. And this simulation here was made with polygons. And so the idea is you have your world, and you have some objects in the world, and generally it will be made out of little triangles. And what you do is you project each of those triangles onto the screen of your computer. And then what you want to do is you want to sort of color in, you want to shade in that triangle with sort of whatever color that triangle should be. And there's all kinds of sort of fancy ways to make this more efficient, of course. But and you have to decide, you know, if I've got two triangles that overlap, I need to know which one is in front of which one is in front of which, and so which one I should draw. But the essential idea is you're sort of going from the world to the screen. And let me contrast that with the ray tracing and ray marching techniques. In these techniques, you go from the screen out into the world. So what you do is you say, okay, here's a pixel of the screen. I want to know what color it should be. And so I trace a ray out into the world and, you know, see if it hits something. And if it does hit something, then I decide to color that pixel the color of whatever it hits, with some other details in there for lighting and so on. And so I've done this both ways, and my sort of more recent work is using these ray tracing, ray marching techniques. And one of the reasons for this, from the sort of mathematical perspective, is in the previous case, I'm going to do it. There we go. So this is the inverse of the exponential map. So you can think of this as you've got your tangent space over here, and you're trying to sort of take objects in the world and project them onto the tangent space. So that's the inverse of the exponential map. This one is just the exponential map. And in some of these more complicated geometries, this map may not be one-to-one, which means that the inverse sort of has problems. So the kind of problems that you might run into, any of these sort of gravitational lensing kind of effects, you're sort of in trouble, because one polygon over here in the polygon rasterization picture has to sort of warp into some number of polygons, and actually each vertex goes to some number of vertices, and there may be different numbers of vertices of pre-images of each vertex for a single triangle. So it all gets sort of messy and difficult. So that's sort of a very brief introduction to the differences between those two. And now let me sort of make the distinction between ray tracing and ray marching. So let me first describe ray tracing. So Pixar movies, every frame is going to be rendered most likely with ray tracing. And so here so you trace a ray forward, and you have to decide if you hit something. And so what you do is, well, usually the things in the space are made up of lots of little triangles. And so you're testing for intersection between this ray and that triangle, which is some sort of linear thing that you need to solve. So it's not particularly difficult, but of course you've got millions and millions of triangles. And so there's lots of optimizations to try and make this more efficient. You can also do ray tracing with, say, a sphere. And now there's two possible points of intersection you're looking for. So now you have to solve some sort of quadratic. But again, this is not so difficult. Now let me contrast that with ray marching, which is what we're actually using. So here, rather than describing geometry with a polygon mesh, we describe geometry with something called a signed distance function. So what a signed distance function does is for each point in space, it tells you how far away is the closest object in your scene. So for this point, I want to know this distance. So in this sort of, say, a simple two-dimensional example, suppose that this circle is centered at the origin, then given some point, the distance to the surface of that object is just the size of the vector from your point to the center of this ball minus the radius of the ball. I guess I should draw some pictures here. So there's R. This is the size of X, and of course, this gives you the right answer. And so what do you do with this signed distance function? It's signed because if you're inside of the ball, then you're going to get a negative answer. So what do you do with this information? So suppose that you're here and you're looking in this direction, and you want to know that you end up hitting the floor at this point here. So well, you start here and you've got the signed distance function. So you ask that signed distance function what value it has, and it says it says that you are within this distance of something, and it sort of tells you a bit more. It tells you that it's safe to move around inside of this ball, that there's no other object of the scene inside of the ball. And so that means I can march along the ray to the next point here, and I know that I won't hit anything on the way. And so if I do that, then I ask it again, how close am I to anything? And it says you're this far, and so you can march forward again, and again, and again, and again. And at some point, you're marching less than some epsilon, and you stop, and you say you've hit an object. And so one of the attractive things about this is that it's quite simple to implement, which is good if you're going to be implementing it in lots of different geometries. I guess let me just give another sort of hint about sort of what makes this nice. We actually don't need to have the exact distance to an object. If we underestimate in some way, right, suppose that we end up with my circles are slightly too small, as long as I sort of underestimate in a sensible way, I'm still going to win. I'm still going to converge eventually. Maybe I'll take a few more steps. And it turns out that in some of the more difficult geometries, maybe it's difficult to get an exact sign distance function to the object that you're going for, but an underestimate is much cheaper to calculate, perhaps. So that's raymarching. And so how do our implementations work? What do we do? So there's a few different ingredients that you need. And I should say, we're currently working on sort of cleaning the code up so that with minimal effort, if somebody else wants to build some sort of scene inside of one of these geometries, or even use these systems for a different geometry that they know about, they should be able to just sort of plug and play and make things work. So what do you need in order to define one of these geometries inside of our implementation? So first of all, you need, so we're looking for a GX geometry. So you need G and X, and you need them to be implemented in a computer-friendly way. So the model has to be written in terms of four-dimensional vectors or whatever it might be. And the group of isometries is probably going to be a bunch of matrices. You need arc length parametrized geodesics in this model. So in order to do raymarching, you need to be able to march along a ray by some distance. And the arc length parameterization gives you that distance. And you need sign distance functions to be able to describe things in your space, like balls and cubes and so on. Now, what else do you need? Maybe you want to show a quotient manifold rather than the entire space GX. If you're in a quotient manifold, then how are you going to describe that quotient manifold in the system? So we use a fundamental domain. So here's a fundamental domain for the torus. So you need some way to describe the walls of your fundamental domain, or to know when you're outside of that fundamental domain. And then when you pass through the boundary, you need some elements of the isometry group G to take you over to, to glue you up to the other side, so you can continue your ray and keep going forwards. And I should mention, this is another advantage of the ray tracing, raymarching methods over the polygon rasterization. So because the map goes forward. So I go from my screen out into the world in ray tracing, say, and when I pass out of my fundamental domain, I just sort of teleport myself to the other side and keep going. If my map goes the other direction, from the world onto my screen, then I sort of need to develop out the entire universal cover before I can start doing anything. I don't know where each individual pixel is going to see. I need to pull everything back onto the screen. And so you need to generate huge amounts of polygon geometry before you can actually draw these things. So it gets much more expensive. But okay, so for a quotient manifold, we also need a way to describe a fundamental domain, and we need some phase pairings. So what else do we need? So if you want to have nice lighting, then there's a few other things that you need from the geometry. So we're using Phong lighting, which is one of the sort of early sort of 1975 computer graphics ways of cheating lighting, but it works very well, and it sort of generalizes nicely to the sort of Riemannian manifold setting. And let me just try and describe a little bit about what's going on with this equation. This is you're here and you're looking at a surface over here which is lit by a light up here, and so you need to know what color that pixel should be. And so the Phong model says the color of that pixel should be a sum of, well, sort of 3 different terms. There's an ambient, oh, and there's kam, kdiff, and kspec. And these are just sort of fractions that are going to add up to 1 of how much you want the ambient light to count versus diffuse light and specular light. And so the ambient light just says, just make it the color of the surface. So each surface sort of glows a little bit. It has a little bit of this color. And then there's these 2 other terms. Let me sort of say something about what these are. So this is the diffuse term, and it's saying, you know, if my surface is lit by this light up here, and suppose the surface is sort of rough, it's sort of a matte surface rather than a smooth, shiny surface, then the amount of light that you get on here is sort of to do with the dot product between the normal vector and the direction that the light comes in. And then finally, there's this sort of specularity. So this is sort of the shininess. So now this is saying how much, if this sort of reflects, here's the reflected light ray, and how close is that to shining in you in the eye? And so there's a term here for that sort of specularity. And so this is sort of, if you only have the diffuse lighting, then your scene maybe looks sort of like this. If you have the specular, then you get this sort of very nice shine, and then you add them all together and you get something that looks pretty good. And I guess I should mention, right, so a lot of these terms that we need, these various vectors that live in this tangent space, they're sort of locally determined. So the normal vector, for example, is really nice and easy to calculate. All you do is you take your sine distance function, you take the gradient, and the gradient of that is the normal vector to your surface where you hit it. The difficult things to calculate are this vector back to the light and the distance here. And so those are the sort of non-local things. And it gets sort of messy, I'll say in a second. You know, there may be multiple ways to take a geodesic from this point back to the light source. And so you need to be able to deal with more than one geodesic there, which again, sort of adds to complexity. But there you go. So the extra thing you need for Phong lighting is you need, for a point and a light source, you need the set of geodesics going from at that point to the light source. And then the 6th element that you need, so how do you set up the screen? So your sort of avatar, your spaceship inside of the space is going to be at some location, and it's going to be facing in some direction. And so you need a frame that you're carrying around with you as you move in your spaceship to decide how to build this screen. So you need to know what the initial tangent vector for all of your rays is, so you can send rays out and see what they hit and so on. And those have to correspond to the screen. And so as you're flying around, you need to carry this frame with you, and so you need to know parallel transport. Right. Oh, and there's a sort of extra little detail here. Suppose that you're in a non-isotropic geometry like H2 cross E. So if you're sort of facing along an H2 direction and E is pointing up above you, and you want to tilt your head back, suppose you're in a VR headset, and look up more in the Euclidean direction, you cannot express that with an isometry of the space, because there's no isometry that's going to swap the hyperbolic direction with the Euclidean direction. So we have to do some sort of extra, we need some extra stuff for the non-isotropic geometries, which sort of keeps track of the orientation of your head separate from isometries of the space. In isotropic geometries, you don't need to do this. But yeah, there's the sixth element. You need parallel transport. So if you can do all of these things and code them up, then this is sort of everything you need to slot into our system. Hopefully, once we've put a bit more work into cleaning things up and be able to produce these things in whatever geometry you want. So I'm just going to show you some postcards from various geometries. This, of course, is Euclidean geometry. Not much to say here, but these are, we're inside of a 3 torus, and it's lit by various lights. And is this sort of showing, we can do balls, of course. This is Boolean operations. We're subtracting balls from the space, and this gives a very nice, nice inexpensive effect. Boolean operations you can do with sine distance functions just by taking the negative of the sine distance function instead of the positive, and these are called the cylinders. In S3, this, I believe, is the quotient of S3 by the 8-element quaternion group. This one is Poincare dodecahedral space, I think, and this is just some fibers of a Hopf vibration. H3, this is Seifert-Weber dodecahedral space. Well, these are both orbifolds. This one, if you go into the simulation on the website, you fly around in the H3 one, you can actually fly inside of here and you see there's cusps inside of here. So there's sort of infinitely many of these little holes approaching a point at the boundary of H3. And this one has sort of hyper-ideal things going on. S2 cross E, so this is, I think this is not actually a quotient manifold. I think this is just putting a ball at each vertex of an icosahedron, I want to say. This is looking down the Euclidean direction. This is looking off to the side in a S2 direction. This picture over here is sort of interesting. So this is, we're looking down on a half space, S2 cross negative numbers, say, which is patterned with the pattern of consonants on the globe. And we are directly above the North Pole. And also there's a light directly above the North Pole. And as we look off to the side, our light rays are wrapping all the way around the sphere, and now we're hitting the South Pole. And you'll see that there's this sort of bright ring well, it's actually just a bright point, but it looks like a ring to us at the South Pole because the light rays are converging at that point as well. And then you look further now out to here, we're wrapping the entire way around the globe, and we're seeing the North Pole again. And again, there's this very bright light because the light rays are all converging again. And that sort of continues as you go outwards. H2 cross C is sort of similar to S2 cross C, but without the interesting sort of reconvergence of geodesics. Nil, this is, I believe, a torus bundle over a Dane twist. And I think this is the same thing again, but right, this one, we're sort of removing balls from a solid space. And so it sort of blocks your view of all of the craziness in the distance. And here we've just got copies of the Earth, and then things get really insane out in the distance. Talking of nil, so this is a simulation where flying away from a single copy of the Earth in nil. So even though things appear to get bigger and smaller and bigger and smaller, we're moving away from it at constant speed all the time. And here's this sort of gravitational lensing kind of weird effect that things sort of split apart. And so nil has this sort of very disturbing feature that if you're looking in the right direction, no matter how far away from something you are, it might look the same size as if you're very close to it. Let me sort of draw a picture that tries to sort of explain what's going on. So the geodesics at least in one model of nil, they sort of spiral around, this blue axis is the z-axis. So they actually spiral as they go upwards. And here what can happen is, so the blue ray is sort of straight ahead of you, and then the gray rays at a bit of an angle away from that, and then the yellow rays an even further angle. And what's happening here, this is producing this picture of sort of rings that you see the Earth in the middle, and then a little bit further out, the gray rays, you don't see anything, you just see the background black. And then you go out a little bit further, you see the yellow rays, you're seeing the Earth again in some sort of ring around you. And so this sort of multiple geodesic thing is the reason for these mirages. This also has an impact on lighting. So here's a scene in nil, which is lit by 3 different lights, I think, the green, the blue, and the purple. But this is lit by only the shortest geodesic. And now it's the shortest 2 geodesics, and now it's the shortest 3 geodesics. So simulating this, you really need to sort of know where all of the different geodesics are in order to get accurate lighting. And this is a video in nil. I mean, a lot of this sort of turns into art. It's like, okay, so what's going on here? What are these Dali-esque shapes? This is 4 different light sources, red, yellow, blue, or was it 3? I think there's a 4th one. I think there's a sort of gray one. And this is like you see on the right here, this is a vertical plane in nil, and we're very slowly moving away from the plane. We're about 30 units away from the light sources, and maybe 1 unit away from this vertical plane. And this very bright sort of area down here is to do with, again, sort of light rays concentrating as you sort of get close to the to one of these conjugate points where you get extra geodesics coming up. Oh, and this doesn't really have much to do with the talk, but I had to throw it in. So just what are the isometries of nil? What do they look like? So here's a sheep and it's getting acted on by one of the isometries. And what does it do to the sheep? It turns out that it shears the sheep, of course. SL2R tilde, so the universal cover of SL2R, is sort of like nil, but even twistier. Whoops, too far. And Sol is also very difficult to understand. I should mention a lot of these pictures, it's very difficult for us to know if we're doing it right? You think you get the code right and you make the picture, and then you see something and you say, is that right? I don't know. It can be difficult to know what's going on. This, maybe if you know anything about Sol, one of the features of it is that as you sort of move up in the Z direction, it squeezes in the X direction and it expands in the Y direction. And so you can see here behind this main pillar in front of us, there's another pillar here, which you can see is sort of very thin across this way and long this way, and it swaps around as you go to the other side. So that's some indication that we're getting the pictures right. There are also some other teams who are sort of working on these kinds of problems. How do you visualize these things? And so we can compare pictures and try and decide if we're doing it right. Okay, so that was the first project in the first half of the talk. I don't know, maybe if there's one quick question before we move on to the second half of the talk, maybe we could do that now, or otherwise maybe we'll just wait until the end. I don't see any questions, so I'm just going to press forward with the second project. So the first project was in all of the 8 Thurston geometries. This one is pretty much only inside of hyperbolic geometry. Again, there's a paper on the archive, and again, there's a website you can go to play around with these. And again, I guess, let me sort of just very briefly show you, what that is. So this is the website, henryseg.github.io/chromology fractals, and you can use the WASD keys to move around and the arrow keys to look in different directions. And you can fly through this sort of infinitely generating fractal. And there's also a control panel up here, which has, well, just lots and lots of different things to play with, different manifolds with different chromology fractals, and there's, well, yeah, there's all kinds of things in here. Slideshow, make this bigger. So, okay, so let me try and explain what these pictures are and what a chromology fractal is. And let me start with a very simple example of the two-dimensional torus. So, so here I've got the two-dimensional torus, and I've got its universal cover up here, so the plane tiled by squares. And let's suppose that you are inside of this torus looking around, and so you're also, I mean, what you see when you're looking around is the same as if you're in the universal cover of the torus. And let me sort of add an extra rule. So suppose that you're here at this dot. This is just another copy of the universal cover of the torus. Suppose you're here at this dot, and I'm going to make this rule that when your sort of light ray passes through the blue arrow, in this direction, things get lighter. So they get lighter and lighter as you go this direction. And as you look in the other direction, as you pass through the arrow, the curve, the blue curve here, in the other direction, things get darker. Actually, let me get rid of the grid. I don't need it anymore. I just see this sort of getting lighter in one direction, darker in the other. And let me actually also add a radius. So there's a radius that you're going to look out to. And then you sort of imagine that you're inside of, you're just looking at the inside of this circle, and it's patterned with the color that you see here, sort of brighter, and then medium colored, and then darker, and then brighter again as you go around. And so this is all of the chromology fractal. So it's a map from the unit tangent bundle of the universal cover of the manifold. So at a point, you're at some point, and you're facing in some direction. And it maps to R, and it depends on the manifold and a chromology class, which we're thinking of just being dual to this circle that we chose. and some radius, right? You have to choose some radius and get out here, and you get some sort of picture on this, well, on the circle around P, and it's, plus 0, minus 0, and so on. And to actually compute this, what you can do, and what we do in our simulation, is we just, we're facing in this direction. We've got some vector v in the unit tangent bundle at P, and we just shoot a geodesic out along that geodesic to distance r, and we count the intersections with, in this case, the circle. Okay, so pretty simple so far. Let's go up a dimension and go from the Euclidean torus to the hyperbolic three-manifold. And the three-manifold we're going to use is the complement of the figure 8 knots. So here's the figure 8 knots. And Thurston shows that you can triangulate this figure 8 knot with 2 ideal tetrahedra. And this, again, is the sort of view in the universal cover of the manifold. And you can see all of the tetrahedra. So, and of course, you see many, many copies of the tetrahedra because they tile through space. I need to replace the blue circle with something. I'm going to replace it with a chromology class dual to a surface. And its surface is going to be made from triangles of my triangulation. This is only one copy of the surface, one elevation of the surface. There really should be lots and lots of copies of the surface, but you wouldn't be able to see much if I drew them all in. So I'm just drawing one connected component of it. So, it's equivalent to just drawing one of these lines that's one of the, well, right, you can't lift this, you have to take an elevation, but we're just drawing one of the lines here. So that's sort of what you should think about the surface. If I take away the edge of the triangulation, you can see the surface a little bit better. And then same thing, lighter when you go through the surface in one direction, darker when you go through the surface in the other direction, and you get this sort of fractal object. And this is, here I'm just putting the chromology fractal behind the surface. And I guess what I want you to notice is that, so this is the same picture, they're just a little bit bigger. And everywhere on here where it's a little bit darker, that's behind the surface. So as you go through the surface, it gets darker. This is a 3D print that David Bachman made that also shows the same sort of idea. So here we've got the Poincare ball model of H3 with one copy of this surface. The elevation is sort of a cutout between the stuff that's solid over here and the stuff that's empty over here. So it's actually sort of 2 copies of this would collide together to give you the whole of the Poincare ball model. And then on the outside, we've drawn the chromology fractal. There's a relation between chromology fractals and something called Canonthurston maps. So maybe looking at the time, I won't get into sort of all of the details of what Canonthurston maps are. Let me just, I guess, mention, this is a figure by Bill Thurston, who of course was one of the people who introduced these maps. Essentially, the way you want to think about this is, so take your surface in your manifold, take an elevation of the surface, so a connected component of sort of the lift of that surface of the universal cover. So it looks like this, and then you sort of take the boundary of that. So this thing is a disk. It's actually a copy of H2 embedded in H3, and it turns out, and this is where the real meat of proving that these things exist, Canonthurston maps. The problem is, okay, you've got this nice embedding of H2 into H3. You would also like a nice map, can't be an embedding, of the boundary of H2 into the boundary of H3. And so that's what this Canonthurston map is. It's sort of squiggling around in and out of these things. And it's actually a sort of natural sphere filling curve. So the circle, which is the boundary of H2, fills the boundary of H3, which is a sphere. I mean, I guess the way that I've described it just made me not surprising that the boundary of that our objects, our chromology fractals, are closely related to these things. But just to sort of show the lineup, the matchup between them. So this is an approximation to this Canonthurston map. Here's the chromology fractal. Here's a version of the chromology fractal where I'm sort of just doing it in two colors, gray and black, rather than the sort of multicolor. The further you go through the surface, the brighter it gets or the darker it gets. Here it's just, did you go through it once or not? And there's the two of them together, and you can see we've got this very nice matchup. But maybe you can see, this red Canonthurston map is sort of not getting in as far. You can see more detail in here, or at least I can. Maybe you can't see on your screen. So we sort of get more detail here. And actually the way that we sort of came across these chromology fractals was an attempt to use kind of pixel-based algorithms to draw better pictures of Canonthurston maps. So you get lots of different behavior, different manifolds. They can show you different things. And just by looking at these pictures, you can sometimes see features of the geometry of the manifold. So down here, for example, you can see this, you've got this sort of Apollonian packing of these circles. And the reason for that is that these surfaces, these elevations, are not these sort of crinkly pleated surfaces. These are just totally geodesic planes. And so they hit the boundary of H3 in circles, and you get some packing. But you get all of this amazing different variety here. I should mention here the colors here. There's nothing special here. It's just sort of artistic license to choose different colors to make it look pretty. So these are all for cusp manifolds, manifolds which have torus boundary. We can also do this for closed manifolds. If you do a Dane filling on the boundary of your cusp manifold, then you'll get a closed manifold. They can still have surfaces. You can play the same game. The implementation has to be a little bit different. We're no longer using ideal triangulations. We have to use material triangulations, where the vertices are inside of the space rather than being on the boundary. There are almost no previous examples of pictures of Canonthurston maps for closed manifolds. Thurston did it for cusp manifolds in the 80s, but these are almost the first examples. If you buy our correspondence between these chromology fractals and the Canonthurston maps, these are almost the first examples of pictures of these things for closed manifolds. I say almost the first example because the very first example is due to Kurt McMullen, who produced this picture back in, I don't know, at least 2 decades ago, maybe 25 years ago. This is an approximation to a Canonthurston map for this. This is a filling of the figure 8 knot complement. And this is our version. And you see once we sort of played around with this enough to get them to line up, we do pretty well at getting them to be the same image. But of course, unsurprisingly, for 25 years later, we get a lot more detail and we can see a lot more of the structure. Let me say something about what the dependence on R is. So I had this radius of this circle, or in 3 dimensions, this circle, the sphere. And it's a little unsatisfying that it's there, right? I mean, it feels like this should be something that depends on the manifold on the chromology class. And I mean, where you are, the point P that your tangent space is based at, your tangent vector V, sure, I can move around in space and I can see different things, but the dependence on R feels sort of artificial. So let me sort of try and say something about what that dependence is, and in fact, how we managed to remove it in the end. So this is a picture of one of these chromology fractals with a very small value of R, e to the 0.5. And so what happens, right? So you're inside of this triangulated space, this triangulation of H3, and you have this small sphere around you. And that sphere cuts through various tetrahedra. And when you pass through faces of this surface, that's when you get lighter or darker. And so these arcs of circles are intersections between the surface that's dual to the chromology class that we're using and our sphere that's around where we are. And so you see this sort of pattern. You really see there's bits of, well, these are somehow bits of tetrahedra intersect with spheres. But of course, if they're not all of the faces between tetrahedra have the surface in them. And so there's sort of, presumably there's extra curves in here which you don't see, which cut this up into triangles or something like that. Now, what happens as I increase R? So here's R is e to the power 1, and your sphere's got bigger. It's intersecting more tetrahedra. You can see there's more of a pattern. It's still blocky. I go to e to the 1.5, and you can see that it's starting to come into focus. And you're starting to see this chromology fractal that I was showing you before. And then at e to the 2, this is sort of, so it's around 8 or so. These are the pictures that I've generally been showing you. Well, what happens if you go further? Here's e to the 2.5, and maybe you can see on your screen it's starting to get a little noisy. And as I go further, e cubed, e to the power 4, e to the power 5, everything just disappears into noise. And so you're like, wait, I mean, surely this was supposed to be some, this was supposed to be some feature, some canonical object, but it appears that it is depending very sensitively on the radius. And is there really anything there if you can't take the limit as r goes to infinity? So what's going on here? This is actually a limitation of our implementation, or at least this version of the implementation. Oh, hello. Oh, there we go. So what's happening is when we're back here, each tetrahedron is occupying a few pixels of the image. And when we go to the next step, each tetrahedron is about the size of a pixel. So you're seeing this sort of variation between neighboring pixels, which is coming because maybe there's a bit of the surface between the tetrahedra in those neighboring pixels. And as you go further, what's happening is that for each pixel, our ray is shooting further through this manifold, it's wrapping around and around the manifold. And neighboring pixels, their rays just get decorrelated. And we only have one sample inside of each pixel, and so they just sort of randomly wander around, and it just turns into noise. So we're sort of undersampling for these larger distances. So what we should be doing is supersampling. So let's see, is this right? Here we go. So this is the right picture. So this is 3 copies, same image, but in this one over here, we're doing only 1 sample per pixel. Here we're doing 4 samples, and here we're doing as much as my graphics card could handle, which is 128 squared samples. And so here R is 4, this is pretty small. Really the only difference you can see between these pictures is that here maybe you see there's a very sharp edge between, right, you can really see the pixels, whereas on the other 2 you've got some anti-aliasing because there's some averaging. When a pixel is contained many different rays which are going into different tetrahedra, you see different behavior either side. So here we are at R equals 6. I'm going to be increasing R in these pictures, and we'll see what happens. Again, they're pretty similar, except that it's maybe a little more nicely anti-aliased in the 4 and 128 squared samples. Here's R is 8. This one's looking pretty nice, as are the other 2. When I go to R is 10, you can see this noise is starting to creep in here. But let's compare 8. 8 is still a little blurry here. It's pretty sharp here. It looks pretty similar here. At 10, this is starting to get a little bit noisy. The 10 is the 1 sample is getting very noisy. At 12, we're starting to lose everything here. This is starting to get a little noisy. But over here, I want you to compare this R is 12 and R is 10. There's not really any appreciable difference between them. And so the supersampling is sort of averaging out all of that noise. We're getting a more accurate picture of what's going on as we increase R. And so we've sort of got 3 main theorems in this paper. The first is that the limit, if you just take this chromology fractal and take the limit as R goes to infinity, in our pictures it was turning into noise, and that's sort of accurate. There's no limit as a function as R goes to infinity. And because your array, it just keeps going forwards and it hits the surface, and it's sort of like you're trying to find the sum of an infinite series of integers. It's not going to happen. You're not going to get a good limit. Second theorem is about what happens inside of one of these pixels. So if you imagine taking a pixel and sort of looking at the sort of distribution of values that you see for rays within that pixel for a certain distance, there's a sort of central limit theorem. So So this is, well, this is a picture here. You can think of this as taking one of the pixels from one of the previous images and just sort of zooming in on that pixel and drawing all of the things that happen inside of that pixel. And it turns out, I mean, it's a fractal, what did you expect? You see pretty much the same thing. And the distribution of values of the chromology fractal that you get has this sort of nice normal distribution. And we prove that, well, so you have to normalize a little bit, divide by square root of r, then the limit is normally distributed. Normally distributed around 0, so we still don't get a picture, but at least we've got sort of this normal distribution coming up. So we're sort of understanding within each pixel what is the chromology fractal do statistically. And then the third sort of realization sort of direction is to say, okay, it doesn't converge to a function, but we should be averaging. And so it should be that the integral of the chromology fractal over a pixel converges even if the function itself doesn't converge. So these are 3 graphs taken at different places, different pixels. So what's going on here? This is so this is the value of the average of the chromology fractal as we increase r. So as we increase r, so this is sort of those very early pictures that were very sort of mosaic-y. And so an individual pixel, it's all one color. So it's sort of just constant and it jumps around as you increase r. And then around here, the sort of mosaic tiles get smaller than the size of a pixel. And then you start seeing this sort of smoother behavior, and eventually it seems to converge. These black lines out here, this is half the standard deviation away from the mean. And so you can see sort of as you, right, so very early on when the pixel is a single color, the standard deviation is 0. And then as it sort of starts spreading out within a pixel, you see this, it looks like square root of r going on here. And these are just 3 different pixels showing that you get the similar sort of qualitative behavior, of course not the exact same behavior. And so this is our third theorem. As r goes to infinity, the chromology fractal converges not to a function, but a distribution on the boundary of the universal curve of the manifold. And so in this way, we're getting this to be actually a sort of canonical object that doesn't depend on r anymore. And it also doesn't depend on sort of which way you're facing. We've now sort of slapped it onto the boundary of H3, if you like. I guess just to finish, here's some artwork. So this is actually this is part of a larger art project with a bunch of people on Twitter to make looping animations which start and end at the checkerboard pattern, and so then they can be sort of all put together in a big sequence. This is called a swirled series. So if you Google swirled series, then you'll see lots of these stacked together. And this is using, this is of course using a chromology fractal. And at the very start, the radius is very small, which means that we see this very blocky pattern, which happens to look like a checkerboard. We had to search pretty hard to find a manifold and a chromology class that would do this for us, but there it is. That is my talk. Again, the paper's down here. Thanks for your attention.
Thank you. So I had some questions. So
Good.
you printed a 3D version of it.
Yes.
But what does that mean?
Well, 3D printing.
No, but if I held it in my hand, what would I understand?
It's not clear what you would understand.
Okay, what would you understand if you held it in your hand? All right.
Right. I mean, we make things, we don't know how good they are going to be in terms of educating, but we make them because of that. Yeah. So maybe I can actually get back to that.
Yeah.
Image and say again, here it is. So what this is so the Poincare ball model of H3. So you can put this surface that I've been talking about, I guess, here's that surface again. It's this sort of pleated, crinkly thing. And here we've cut the Poincare ball model in half along this surface. And we've thrown away one of the two halves, I guess the darker half, because you can see on the outside, it's all getting very bright out here. So, so I guess what I would understand is, okay, this is a physical representation of this surface, of an elevation of the fiber of the figure 8 null complement, and you can see how it's pleating, and I guess one could use this as an aid to if I was doing this in person and I had one of these things, then maybe I would sort of use this as an aid to say, okay, if I fly through this, it's going to get lighter. If I go in the other direction, it's going to go darker.
These little like onion things. So like,
this
yeah.
stuff here.
Yeah, exactly.
Let me actually show you this in real time. So if I go to, maybe we should do a demo. So one of the really cool things you can do, let's what am I doing? So I want to turn on an elevation, and let's turn off the chromology fractal. So, and let's increase the number of steps. Okay, so so here, flying around inside of space, this is the surface, and there's one of those onion rings, right?
I see.
It's this very, very pleated thing, and there's some sort of, we're close to a cusp of the manifold, and so somewhere up there, but if I try and drive towards it, things will eventually break, but there's a cusp of the manifold that in some sense is close to you, and in that direction.
I see. Okay. So it becomes pleated, and that's why it looks like it has all these layers there.
Right, right.
I see.
With a different version of the surface, you would of course see something different.
And then you had said this interesting thing that you draw things and you're not sure if you got it right.
Sure. Yeah, I mean, the code could be wrong.
But how could you do something once you're in that space? Can't you detect if you're in that space? Can't you actually walk around and decide if it's right?
So this is for the other project. So let's go over to the other project.
Yeah, exactly. Yeah.
Let's fly in the H3 project. This is a nice, some of these are very taxing on your graphics processor. But this one is not bad at all. This one's, I can run on a very big screen and it's fine. So yeah, so in H3, we know what's going on, right?
Sure.
Because things are relatively simple. When it gets towards the harder ones, which haven't been visualized before, then it gets more difficult, right? You see something off in the distance, which looks sort of strange. It's like, why is that? It looks like I've got an edge to the, like maybe I'm supposed to be looking at the XY plane, but it looks like it ends in a strange way. And I don't know if that's a bug in the program or if that's what it actually looks like, right?
Mm-hmm.
And if you fly towards it, it disappears because it was just a mirage. And,
I see.
And you don't know, right? You can't get close to it because it's some feature of the way that geodesics at distance are interacting. And so
it's not just geometry, it's actually what you'd see. And so you're not sure.
Right. And I mean, so it's a process. You see something and then you say, is that right? Or is my code screwed up? And you try and work out, maybe by hand, in that situation, what should happen? And then you decide if your code is screwed up or not. And hopefully our code is not screwed up, but it's a little difficult to tell with these stranger spaces.
I understand. Okay.
Could I ask a related question?
Yeah.
Yes.
So with respect to the first question, where you have a 3D printout of these complicated spaces and try and interpret it in 3D, I'm going to flip it a little bit. In the 90s, I used to work on display holography, where we would create anamorphic images and pre-distort, and then we'd expose holograms, and the substrate would be on curved or flat surfaces. And then you reconstruct the original, the pre-distorted wavefront would be then distorted depending on what surface you place that holographic substrate on. And and that's usually done for some of the reasons that you mentioned, but in a kind of warped way, so that the viewer can then see the undistorted version that was intended. But I've also seen people, mostly artists, play with holography to try and visualize what a 4D space would be like. And the thing that's interesting is when I've seen people look at orthoscopic and pseudoscopic spaces, they can shine the carrier wavefront in the opposite direction to create a real image. And in normal conventional optics, a real image is you just focus on a point or focus on this.
Mhm.
In this case, it would focus on trillions of points and create a wavefront of whatever shape you want. And so what I'm wondering is the kind of combination of the 3D printout and your VR walkthroughs, would there be any interest or value in creating a real image of that space?
So I'm not sure I quite understand what real image means in this.
Sorry,
in this
real image.
context.
Sorry, that's a very specific term. All that means is
Okay.
if I have like, here is your viewing frustrum and here's the
Mhm.
plane through which I see. A virtual image means that the light is coming to my eye through that plane, whereas a real image means it's focused so that I can pass my hand through it.
Oh, I see. Oh,
Right.
well, let me say something and maybe it'll turn out to be what you
Please.
mean. So, so what you could do is say, so you're in this three-dimensional space with geometry, but really what you want to interact with is things you want to interact with things in your tangent bundle. So I'm sitting in a place, and I imagine that, you know, my camera is looking out into the world, and I'm dragging objects back by the inverse of the exponential map into my tangent space. And then in that tangent space, maybe I don't even have to put my head at the origin. Maybe I can look around them or touch them or something like that. One of the other groups thinking about these things, Eric and Dorota, they have a complicated Polish name, but Hyperrogue is the project that they go with. And they're thinking more along those lines. They're going much more along so the issue with this is that you have to use, as far as I'm aware, you have to use the inverse exponential map, right? You have to map from the world into your tangent space. And when that's not single valued, that gets messy. So all of our stuff is going the other direction. We've thought a little bit about that, but nothing sort of jumps out as here's how to do it and get something in. But I mean, essentially, you know, it's always this problem of like, you're trying to grab this thing which has weird geometry and pull it into a Euclidean space where we have a chance of understanding it. And it's not always, well, it's not always easy, and you might not like the results. It might not help you understand what's going on.
Thank you.
Other questions? Just talk or raise your hand.
Right. Yeah, I have a question. You mentioned that if you were in, say, S2 cross E, and if you're looking in one direction, yeah, you see something's curved, and then if you bend your neck up, it goes into the straight direction, and so
Right.
those are always distinct. So, in a sense, you know, if the space is not a space of constant curvature, then you're always facing this. You use the metaphor of flying through it in a spaceship, but if it's not of constant curvature, that spaceship would warp and bend, and like we believe we live in bodies made of flesh. We're not used to that kind of. So, well, I mean, with all your experience, do you have a response to, or I guess in a sense, what you're doing is you're just a disembodied eye as one point that's looking through?
So, right. I mean, of course, it's a simulation, right? And we can do whatever we want. But it's not that unreasonable to imagine, like, so let's take a simple example. What would it be like if you really were inside of the three sphere, say, and you tried to move around, or H3? Let's take a simpler example. And so, well, so as you move inside, suppose you're moving forward in S3, well, you know, your head, your arms are trying to move forward and keep their distance apart from each other, but the geodesics going forward converge. Mm-hmm. So as you move through the space, you're going to feel a force, which is an apparent force, which is kind of pulling, you know, pushing in on you. And if you're in H3 and you're trying to fly around, then there'll be a force which is trying to pull you apart. But if you're made of squishy bodies, that have, bonds between them, then you just deal with it. I mean, it's like, dealing with centrifugal force. If you're in a rotating frame of reference, then there's apparently a force on you that you have to deal with. Or if you're near a black hole and you're getting sort of, what is it called, the different amounts of force on your feet and on your head, as long as it's not too strong, as long as you're not, too strong, then you just deal with it, and presumably would just deform. So like, it's not out of the question that you could evolve life in S2 cross E that could even turn, I think. You just have to deal with the forces that happen because the curvature is changing.
If I remember right, it's 3G, right? If your feet accelerate at 3G compared to your head, you tear in half.
Okay, well, yeah, don't do that much.
Yeah, that was a homework problem in relativity.
I mean, it's a simple, like, suppose you're trying to be an animal inside of H3. How big can you be? Because the bigger you get, the harder it is to move without tearing yourself apart.
That's right. That's right.
Or maybe, you should move, instead, the way that you move is maybe you're a blob, and, you can expand out in this direction and shrink in this direction, and that's fine. You can just sort of concertina along, and you never actually have to all move at once in the same,
I understand.
Along geodesics and tear yourself apart.
Henry, I have a question about the technical aspects of coding all of this up. I mean, imagine if instead of a single manifold, like the kind you're trying to visualize, you had a union of 2-3 manifolds along a surface that intersected transversely. Could you do that whole inception thing where you go up to the singularity and change and then walk up the other manifold?
We've thought about it. I mean, right. I mean, in my slides, where are my slides? I've lost my slides. I mean, there's this list of ingredients you need. If you can provide me with, where is it? Here? Yeah. If you got all these ingredients, we're good to go, right? I mean, so, they might get more messy to calculate, right? You might need to do, like, I mean, as much as possible, all of our functions are, closed form. You want very nice, efficient things. I mean, so if you just want some completely arbitrary metric, so here's the thing that I would love to be able to do: sit inside of a manifold and see what happens as Ricci flow acts on it. Right? What does it look like? How is the space deforming around you? But to do that, of course, you can't do it with closed form. You need everything to be numerical. But in principle, there's no reason you couldn't get a good approximation, I think, of what it would look like. You just have to be able to write it down in some way that you can actually calculate.
All right, thanks.
Other questions? Well, I want to thank Henry. I want to thank all our speakers this semester. I got a message. Yes, thank you. I got a message from my department chair saying, you really should take a real vacation this you should really tune out in December. So I'll pass that along, and I'm supposed to do it, and I'm supposed to recommend all my students and postdocs do it. So I hope everybody gets a restful break, and we'll come back next semester. We'll let you know what's happening.